Today's lesson is on property of linear relations. How can we know a relation is linear? Well, what we saw last day was if we go ahead and graph the points, we see if they line up, and it's very obvious if it's linear or nonlinear. So the best graphing is the best way, but it may take a little bit of time. So here's our two key ideas for today. Two key ideas for today are: what does it mean for points to line up? And maybe more importantly, what has to happen for points to line up? Something has to happen. So let's look at a real life example of renting a car. So here's my story. Today we're going to rent a car and we're going to represent it by letter C, capital C. And the cost of renting the car depends on the number of kilometers you've driven, D. The initial cost to rent a car is $25, and then you have to pay $20 for every 100 kilometers driven after that. So this is kind of a typical car rental agreement. So in this one right here, the dependent variable is the cost. The cost of renting a car depends on how far you drive. The more you drive, the more it costs. The less you drive, the less it costs. So cost is going to be our dependent variable. And the dependent variable is always the y coordinate. It is always the second column in a table of values. So this has real meaning. There's not really x and y associated with it. We're calling them D and C, but it's similar to a mathy table of values. Now in this case, the distance is the independent variable. And, and we always have the independent variable is always represented as your x, and it's always the first column. So we have to agree on this. This is our convention. So just like last day, we can make a table of values with reasonable numbers. So I'm going to pick these numbers. These are really simple. They're simple to find, to calculate how much it would cost if we drove this far. And again, simple to graph as well. So if we rented a car and didn't drive anywhere, that would cost $25. If we rented a car and drove 100, well, it would cost us $25 plus $20 for the 100. If we rented a car and drove 200, it would cost $25 and 2 times 20. So again, the cost would equal $25 plus 2 times 20. The 2 represents the 200. And this would be 65, and I'm just going to fill in the rest really quickly. So here would be our table of values that would represent the cost. And again, what I want you to notice is that there are some patterns in this column, in these columns. So this one over here, this is always going up by 20. So from 65 to 85, from 85 to 105, etc. So in this column right here, we notice a pattern. And in this column right here, well, even though I made up the numbers, there is a pattern in this one too. Now, by picking nice numbers, we can actually see this pattern really easy. If I had to pick silly numbers, it would have been really, really difficult to notice the pattern. So again, what do we notice? Well, we notice in the first column, which is distance, but we're just going to treat it as the first column. The first column is increasing, meaning it's getting bigger, is increasing by 100, as the second column is increasing by 20. So there are patterns, but these patterns are connected, right? Once you change one, you change the other. So in this table, whether you realize that this is a linear relationship or not, if we can find a pattern in a table, that's going to tell us it is linear. So again, a linear relationship has a pattern in the table, and by that pattern, it has to be in both columns. Now the numbers don't have to be the same, right? This is up, increased by 100, increased by 20, but the pattern has to be the same. Plus 100, plus 100, plus 100, plus 20, plus 20, plus 20. So a table of values is easy to construct. We did that We've done that quite a bit, and it actually points something out. Well, you can also see this relationship in ordered pairs. So if we group these like coordinates on a grid, then I'm not going to do them all. I'll just do the first few. So again, what you should notice is there's also a pattern when we go from 0 to 100, 100 to 200, etc., 200 to 300. Here's our plus 100 pattern. There's our plus 100 pattern, etc. And underneath, here's our plus 20 pattern, our plus 20 pattern, and finally, our plus 20 pattern. So again, what we see is we see a pattern in our ordered pairs. And again, it's not first column, second column. There's a pattern with the first numbers, and there's a pattern in the second numbers. And again, here's what I mean. Here's our first numbers, there's a pattern. And here's our second numbers, that's a pattern. So this is like x comma y, there's a pattern. So again, I've been saying that this is going to be a linear relationship, but let's actually go ahead and see that it will be a linear relationship. So again, this is going to be our cost, and here's going to be the distance driven. And I'm just going to scale it. I'm going to break the graph. I just want to do this one time. It's never really a good idea to break a graph, but I'm just going to do it right now, just so we can fit as much of this on nicely. So I'm going to start at 25, and I'm going to scale 35, 45, 65, 85, 105. And I'll just go that far. And here, each little section will be 50. So we go 50, 100, then I'll jump up to 200, 300, 400, 500. And I won't put 500 because that won't fit. So again, when we go ahead and plot this, we have 0, 25 from our table above or from our ordered pairs above. We have 145, 265, 385, and 400, 105. And again, what I hope you notice is, again, there is a pattern. There is a pattern in the graph. And again, the pattern in the graph is they line up. So the moral of the story is what has to happen for there to be a linear relationship, and what has to happen for there to be a linear relationship for points to line up. What has to happen is you have to have a pattern in the x and the y, or a pattern in the table of values, or a pattern in the graph. So this leads to this new property, and what it's called is, this new property is called the constant rate of change. And I'm just going to mention it now, constant rate of change property. And we're going to talk about this a bit as we go through the next few lessons. And here's all the constant rate of change property is. It's the pattern. Now this is exactly what it is, and this is exactly how you have to think about it. It is the pattern as y changes remains the same, meaning if we're always adding 20, adding 20, adding 20, the pattern remains the same as the pattern as x changes remains the same. And when you do that, what you get is a linear relationship. So this is what has to happen to get a linear relationship. You have to have a pattern in the y, and again, it has to be a constant pattern. It has to be the same. And you have to have a pattern in the x. And again, it is y compared to x. That's really important. So this is called the constant rate of change property. And if you find that there's constant rate of change, you don't have to draw the picture anymore. You just have to say, hey, there is a constant rate of change or there's not a constant rate of change. So let's look at a quick couple of questions and decide, is it linear, yes or no? So again, worst comes to worst, we could graph it. So let's look at our table of values. A new car is purchased for $20,000. Every year it depreciates by 20%. The value of the car is related to time. So the value of the car depends on how old it is. So at time zero, when you just bought it, your car is worth $20,000. Well, a year later, it's gone down by 20%, or it's only worth 80%. So if we multiply 0.80 times 20,000, we're going to get 16,000. So after 1 year, it's only worth 16,000. But again, the next year, it's going to, again, depreciate by 20%, or it's going to be worth 80%, but it's worth 80% of what it was before. So when we multiply 0.8 times 16,800, we get 12,800, and I'll fill in the rest. I'll fill in the last two columns, and here's what we get. And in this one right here, I would ask, is this a linear relationship? And there's two ways to answer the question. Well, the first way, we could graph it. So let's plot the value. And I'm going to scale it in 2000. So here's 2000, then jump up to 10,000, then jump up to 20,000. And time in years, here's our time. And this is going to be now 1 year, 2 years, 3 years, 4 years, etc. And when we plot those points, here's what we get. Now it's 20. After time 1, it's 16. After time 2, it's 12 to 8. After time 3, it's a little over 10,000. And time 4, it's a little over that. And if you looked at that picture, that is not a line. In fact, I'm going to try to connect the dots. But if you put a ruler onto your dots, you're going to absolutely see it is not linear. So this example of this car getting, depreciating, losing value is not linear. And we can say, well, see the graph. But also, what you want to also see in the table is the change in y. So in the y column, the value, the change in y, which in this case is the value of the car, is not constant. So the first drop is 4,000, and then the next drop is 3,200, and then the next drop is 2,560, not a constant. Now there is a constant change in the x, but remember, for something to be linear, we have to have a constant rate of change, which means both. So not linear pictorially, not linear using our table. Well, let's look at another one. For a surf call, technician charges a flat rate of $75 and $50 for every hour he works. The total cost of the service is related to time. So the total cost of this person coming out, the cost depends on the amount of time. So the more time he's at your house, the more it costs you, the less time, less. So again, you phone him up and he says, I'm going to charge you $75 right off the bat, and then $50 for every hour I'm at your house. So here's our table of values, and that's what it looks like. So if we go ahead and graph this, well, we'll graph the cost. Remember, the second column is always your y. The first column is always your x. So here's our 1 hour, 2 hours, 3 and 4. And we'll scale in 25s. Again, you don't have to write them all out. That gets really messy. Show me your scale, and then I know what you're doing. So this one right here, okay, you initially get charged $75. 1 hour is $125, $175, and here we go. So in this case right here, the points obviously line up. So is this a linear relationship? Yes, it's linear. And how can we tell? Well, again, you see the graph, the points line up, but also the change, if we look at our table, here's our change, plus 50, plus 50, plus 50, etc., as we add an hour, as we add an hour, as we plus 1. So again, the change in y and x are both constant. The change in y and x are both constant. And that both constant is important. If one is changing and the other one isn't, like the example above, not linear. We don't actually even have to draw the picture. So here's one last example. Determine the rate of change of the following and what it represents. So here's a little picture, and it's the amount of gas remaining versus distance driven. So again, the further you drive, the more gas you burn. The less you drive, the less gas you burn. So the amount of fuel you use depends on how far you driven. So this point right here represents a full tank of gas, right? That's what that represents. At time zero, or distance zero, you have 50 liters in your tank, a full tank of gas. And this point right here, again, we are totally empty, so out of gas. So what we basically want to do is we want to determine the pattern. So in order to find the rate of change, the best way to think of the rate of change is find the patterns. Find the patterns in y and x. And remember, it matters. We're always looking at y first. So again, I'll make note of that. Again, what we want is we want y to x. Well, we don't have a table of values here. We could make one. But if we think of y is the vertical axis. So we're going to compare y to x, vertical to horizontal. And in this case, we're going to consider volume to distance. And again, what we should notice is the volume goes from 50 to 0. And the distance goes from 0 to 700. So our rate of change, remember, rate of change is a straight line where rate of change means constant pattern. The rate of change can be expressed as a fraction or a ratio, but we're gonna try to express it as a fraction. So here's what happens from start to finish. We use 50 liters. So there's the negative, right? We started out with 50 and we went to 0. We've gone down by 50 as we drive that far. So this is our rate of change. And again, instead of looking at it like the whole trip, we could simplify this to dividing both numbers by 50. So we can cancel out a 50 on top and a 50 on the bottom. And again, what we'd have is that. So really what this represents is how much fuel the car burns as it drives. So one way of saying what this rate of change is the car uses 1 liter of gas for every 14 kilometers. So today we've talked about properties of linear relations and what has to happen. So that it might seem a little bit complicated, but really all we've done today is look for patterns. It's very obvious to see a pattern in a picture. The points line up. But the table really shows you numerically what the pattern is. As we go through this unit a little bit, starting next day and the day after, we're going to look at it pictorially, how to figure out the pattern. But whether you figure it out pictorially or with arithmetic from a table, linear relations have a constant pattern. If we have a constant pattern, the points line up and we can connect those points with a straight line.